15 degrees outside. Inside the engine, temperatures exceed 1,500 degrees. This extreme temperature contrast is not a problem. It is the goal. The greater the difference between the cold outside air and the hot core, the higher the engine's thermal efficiency. In simple terms, better efficiency means less fuel burned. According to thermal efficiency theory, there are only two ways to improve this: fly in colder air or push engine temperatures even higher. Here's a critical fact. Modern aircraft engines already operate at temperatures about 250 degrees higher than the melting point of their own materials. Every day, more than 10,000 aircraft fly using this technology. Its full name is the jet turbine engine. At the front is a massive fan, pulling in 1.3 tons of air every second. Most of this air bypasses the core and exits directly from the rear, generating efficient thrust. A smaller portion enters the central compressor. Here, the air is compressed 50 times, raising its temperature to 600 degrees. Next, the compressed air flows into the combustion chamber, where it mixes with fuel and ignites instantly. The explosion creates an enormous jet of energy that rushes toward the turbine at the rear. The turbine blades spin at extreme speed, converting this energy into thrust that pushes the aircraft forward. This is where conditions become brutal. The turbine blades inside the combustion zone endure temperatures of 1,500 degrees. At the same time, they rotate at 12,500 revolutions per minute. At that speed, the blade tips cut through air at 1,900 kilometers per hour. Each blade weighs only 300 grams, yet it must withstand a pulling force equivalent to 20 tons. And it must do this while glowing hot. There's a problem. The blade material itself can only tolerate about 1,000 degrees. At 1,200 degrees, it would completely fail. So how does it survive at 1,500 degrees? The answer is precision engineering. First, microscopic cooling channels are built inside each blade. Cool air flows through these channels, carrying heat away from the core. Second, the blade surface is drilled with thousands of film cooling holes. Cooling air exits through these holes, forming a thin insulating gas layer that shields the blade from direct heat. This alone can reduce the surface temperature to below 1,100 degrees. Third, the blade receives two protective coatings. The first is a metallic coating that prevents oxidation. The second is a ceramic thermal barrier. Ceramics are exceptional insulators. This layer lowers the internal blade temperature by another 170 degrees. Together, these systems allow turbine blades to operate reliably in conditions that should be impossible. Now, this is how those blades are made. What you see here is the wax mold used to shape the blade. This is the raw wax material, and this is the mold itself. The wax is injected, forming an exact blade replica. These wax models are then connected in groups of 4. Next, the entire assembly is coated. The wax structure is dipped into a slurry, then repeatedly rolled and layered. After that, a uniform layer of sand is applied to form the outer shell. The shell is left to air dry. Once hardened, it is baked at high temperature. The wax melts and drains away, leaving behind a hollow ceramic mold. This becomes the final casting mold. Molten nickel-based superalloy is poured inside. Nickel alloy is ideal for turbine blades. Ordinary metals may be strong at room temperature, but around 600 degrees their internal atomic structure weakens and softens. Nickel-based alloys are different. Inside, their crystal structure is dense and highly ordered. Like a rigid three-dimensional grid, multiple elements form a cubic lattice that resists deformation. Forcing this structure to change requires enormous energy. This is why nickel alloys maintain strength at extreme temperatures. These alloys are used at the very core of the engine. They drive the high-speed turbine shaft, power the front fan, and keep the compressor running continuously. They are a decisive factor in engine performance. The principle of a turbofan engine is not complicated. What separates one engine from another is technology, cooling efficiency, manufacturing precision, and above all, materials.